Welcome to Math 31. This is lesson 5 where we start looking at the limits of trigonometric functions. So everything up till now has just been getting your chops together, so to speak. And now we cover some calculus topics. The limits are themselves quite interesting because we have to review the basic methods for evaluating limits, because that's really what we're doing. No departure, except that we have a little bit more information now to handle trigonometric ones. So to start things off, let's just consider a regular sine curve looking like this. And if you were to analyze this by inspection, not do a little bit anything too fancy, by inspection, the limit of sine theta as theta approaches 0 is going to be equal to 0. So as you get closer and closer to this value, the y value, as x gets closer and closer to 0, y gets closer and closer to 0. So the concept that I'm illustrating here is that limits with trigonometric functions, it's not black magic or voodoo or anything like that. It works the same way as everything else does graphically. And in fact, you can muscle your way through trigonometric limits. You can also graphically solve them. And they work really the same way as everything else does. And the same thing with cos too, right? So for the cosine curve, same wave as sine, just it's got a different horizontal orientation. And if you were to take the limit of this function as theta approaches 0, well, you'd see that we're getting closer and closer to the y value. So it's equal to y. Or equal to 1, excuse me. So the y value is getting closer and closer to 1. Now these two illustrations were with the angle value, the x-coordinate approaching 0, but the same thing would be true if you were talking about there, for example. The limit of the cosine function as theta approached pi is equal to -1. And because it's a continuous function with no gaps or anything like that, they're usually pretty easy to work out as long as they're nice simple functions like this. Where things get a little bit more complicated is where we add something to the mix, and we unfortunately have to do so. So if you're given this one, the limit as theta approaches 0 of sine theta over theta. Now if you were to, without even writing this down, if you were to substitute 0 in for theta, you would get sine of 0 over 0, and that is undefined, or excuse me, that's 0 over 0, which isn't going to work for you. Now if you think back to our old limit methods, when you do get 0 over 0, it means you have to keep on going. So I'm not going to write that down, but I'm going to make that casual observance and file it away someplace, because it will come to play soon. But what I'm going to do is set up a table of values and just substitute values in for theta just to see what happens. Starting off at theta is equal to 1. Now be in rad mode, and I'm just going to push these through the calculator and see what I get. So the sine of 1 rad divided by 1. Now make sure you close your bracket. I know you don't need to be told that, but just in case, sine of 1 divided by 1, and you're going to get about 0.84. And then, pick sine is equal to 0.5, pick sine is equal to 0.1, 0.001. Maybe try negative 0.0012 to take it from the other side and see if we're getting, if this sheds any light on the situation. So here I'm getting 0.96. Then sine 0.1 divided by 0.1 is 0.99, and then sine 0.001 divided by 0.001 is 0.99999. Many nines. Try the negative. Sine negative 0.001 divided by negative 0.001. And, we're getting the same thing, strangely. Now, I'm going to make the assertion that by inspection, or by substitution, the limit as theta approaches 0 of the function sine theta over theta is equal to 1. It seems reasonable, and in fact, if you were to graph this one, just y1 is equal to the sine of x divided by x, I think you'd see that it also does appear to be approaching 1. Now, where this is going is a rule. Never mind that I've written over top of it. But the limit of sine theta over theta is equal to 1. Important enough to put a box around it. And then this is also true because the reciprocal of 1 is just 1. The limit as theta approaches 0 of theta over sine theta is also equal to 1. And this is on your formula sheet. And we're going to use it a lot. So even though it's on your formula sheet, which you want to keep around, it also is something that you want to memorize. And you'll work with it enough that you probably will have it down. So it's very important. Now if we take a look at this one and do the same thing. Now if you did plug in 0 for this, you would also get 0 over 0. 1 minus cos of 0 is 0, and cos of 0, and then over 0. So I plug in values closer and closer to 0, and we don't have to get too carried away here. How about 1.5? Let's go to 0.1, and then 0.001, and then negative 0.001. And see what we get. Now make sure on your calculator, and again I don't think you need to be told this, but 1 minus cos of 1, for example, bracket that, but then press enter, or else put a bracket around the whole thing so that you're dividing the entire numerator by the denominator. So nowhere, you're not getting too much from the first substitution. And then 0.24. Then 0.04995. Then you're going to get 5 times 10 to the negative 4. That's a small number. And then I think you're going to get the same thing on the next one. So there you have it. So what is ending up going on, I think, by inspection of this is that it is going to be equal to 0. It's getting closer and closer to 0. So by inspection, the limit of this function as theta approaches 0, 1 minus cos theta over theta is equal to 0. And we don't need to go any further, I don't think, with that. Now that is a negative there, in case you didn't see that. Now if you graphed it, you'd get, I'll do it at the bottom, y1 is equal to, open bracket, 1 minus cos x divided by x. And then this graph appears to support what we just saw. looks like more like a regular sine curve as a result of that. And where it's all going is this. And this is another limit form that we're going to use a lot. Now the reciprocal is not true, but because the reciprocal of 0 is undefined, so we can't do that. But this would be true. Sometimes you see it as cos theta minus 1 over theta still equal to 0. And this is on your formula sheet. In fact, I think I've got it written the second way on your formula sheet. But both are true, and so you have to be comfortable with identifying either one of them. Now where we're going is evaluating a bunch of different limits, mostly working with these two forms, although there's another one that's going to affect us later on. Oops. So to evaluate trig limits, use regular limit methods. Ignore that 0 over 0 for now. You always substitute in the value. And then if the expression equals 0 over 0, this tells you that the expression can be simplified. So you go on with it. Now, if you do sub the value in and you get a number, then you're done. You've got an answer. Or you might get no limit exists if you get something like 5 over 0. So remember back to the possibilities. And then we use the given limit form. So by that I mean those two ones that we've just covered, where the limit of sine theta over theta is going to be equal to 1 when theta approaches 0. And then the one with cosine. Now those ones worth noting are we're approaching 0, and you don't always approach 0. So that is important. Most of the ones we do work with will be, however, but always be prepared for any substitution. We'll see quite a few of those too. So let's do a few. Let's evaluate the following limits. So the limit of sine 3x over cos 2x as x approaches 0. So to start it off, we just sub in, and we see where this takes us. The sine of 3 times 0 over the cos of 2 times 0 is the sine of 0 over cosine of 0. Now the sine of 0 rads, if you think to your unit circle or use your calculator, is equal to 0. But the cosine of 0 is equal to 1. So this whole thing is equal to 0. So that's not too bad. Pretty straightforward, in fact. And if you did graph this, you'd see that this is true as well. Now this one's more complicated because if you substitute it into 0, you'd get sine of 9 times 0 over the sine of 5 times 0, which is sine of 0 over sine of 0, which is equal to 0 over 0. So you must simplify. And you usually cannot factor the way you would a polynomial or a rational expression. We have to use what we know about trig limits to work this out. Now the thing that you can do with this is use a method that's often called as breaking up. So break up the expression. Now this is about as long a way to solve the problem as you can use. So many of you will shortcut it after a while and recognize the patterns and work it out more quickly. And that's fine. In fact, I encourage it. But the longest method is also pretty reliable. And by breaking up the expression, what I mean is that we take this one and we take the sine of 9x, keep that there, and we note that that's multiplied by the denominator of sine to the 5x. So I keep each term separate. And the reason for this is that I want to express these in the form sine A over A or A over sine A. So that's what it's all about when you've got sine functions. And by breaking it up like this, I can put it in that form by introducing the terms that I want, as long as I'm careful not to break any math rules along the way. So when I look at that sine 9x on top, I'm thinking, well, if I bring in a 9x on the bottom, that's going to turn that part of the expression into 1, because the sine of x over x is equal to 1. So that's good. And then that sine of 5x in the bottom, I'm thinking the same way. If I bring in a 5x on top, then that expression is going to be 1. Now the only problem with that sort of thing is that you just can't go introducing 5x's and 9x's all the time. So you have to balance it off. So if I have a 9x on the bottom there, I introduce a 9x on top there. And the same thing with the 5x. I have previously brought one in up there, so I bring one in at the bottom. And that means I haven't done a thing. So the x's cancel out, and then I end up really with just a net change of 9 over 5. And then when I multiply this whole thing, the limit will then be equal to 9 over 5. So it works pretty well. Very reliable method. Now you can shortcut this quite a bit. Some of you, by the time you get to an exam on these, you'll look at it and you say, well, really all I did was I put a 9 on top and then a 5 on the bottom. And, you know, stuff like that you can do fairly quickly. These wouldn't be worth an awful lot of marks. But you do want to be pretty much 100% accurate with them. So you want to make sure that whatever you do is correct mathematically, for one thing. You don't want to sort of invent your own patterns that aren't reliably there. But you also want to be, you have to be very accurate, and you have to be mathematically correct. And this one would work the same way. Or I don't want to jump the gun on this one, but if you did plug in 0 over 0, you would get 0 over 0. So this one must simplify as well. So what we can do is take a look at this expression and break it up again. So my numerator is the sine of x over 2, or 1/2 x. And then over there we've got the x. Now I'm going to do this two ways, a real long way, and then I'm going to clean it up a bit. So the long method would be, it's broken up like this, or it looks like this. And I say to myself, I will bring in an x over 2 on the bottom to make that equal to 1. And then this one would require an x over 2 on top to balance it out. And then all you do is clean up that x over 2 over x. So x over 2 divided by x is x over 2 times 1 over x, meaning that you're canceling the x's out. And then really all you've got left over is 1/2. So that's correct, and it works. But to make this go a little quicker, you may prefer, and this would be recommended, do a little less work. Because if you keep it in this form, first off, you can see that there's no need to introduce an x on the bottom because there's an x already there, and that's what I did. That was a little bit of overkill. So all I really need on the bottom is a 1/2, because this is the same, 1x over 2 is 1/2 x, right? So you don't need to bring in an x if it's already there. So just bring in a 1/2, and then all you're doing is bringing in a factor of 1/2 on top, which can be just written as a regular fraction. And then that's a little faster. So 1 times 1/2 is equal to 1/2. It's not a big deal, but if you have terms already there, no need to introduce them. So just bring in what you don't need. So number 4, a little bit more complicated looking. And you may want to take these ones and pause me and go through it yourself. But when we substitute in, by the way, you're going to get 0 over 0. I won't take up a lot of airtime to do that, but it will work like that. Now I'm going to go all the way with this one. I'm going to break it up into 1, 2, 3 components. So this is the limit as x approaches 0. See, 3 on the bottom is really a factor of 1/3. And then that's going to be multiplied by sine of x over 5, multiplied again by sine of 4x on the bottom. Now I'm just going to bring in what I need, which is an x over 5 down there, and then a 4x on top. And I know that based on what I know about sine limits, those two are going to be equal to 1. So that's the form I want. But of course I have to now balance things off because I need to have an x over 5 brought in on top to balance the 1 on the bottom, and then also a 4x. So this is x over 5 divided by 4x, so times 1 over 4x. When I simplify this, will give me 1 over 20. So 1 over 20 is there, times 1 times 1. And then times 1/3. And then that's equal to 1 over 60. So it looks complicated, but it isn't really all that bad. Let's try a few more at least. Let's cover some more variations. So we get the limit of x plus tan x over sine x. Now, when you substitute 0 in, you're going to get 0 plus tan of 0, which is 0, over 0. So it also is going to be of that form, 0 over 0. Now, you can really do a couple things with this, but I think when I see a numerator on the bottom, I would write this as I would split up the expression. So x over sine x plus tan x over sine x. So those are two separate limits, actually. But x over sine x is nice because that is just 1. And then if we do the algebra on the tan x over sine x, that's sine x over cos x divided by sine x, so times 1 over sine x, is 1 over cos x. So I'm just going to break this into, back this one up. I don't want to get too carried away here. This, I'll still write this as x over sine x plus 1 over cos x. Now I'm going to take the limit, and that will give me 1. And then as x approaches 0, the cos of 0 is going to be 1, or the cos function will approach 1. So it's 1 plus 1 over 1, which is equal to 2. And so we have that one worked out. Number 6, cosecant theta times secant theta minus 1 over secant. This is an interesting one because when you do substitute in, you run into not the 0 over 0 problem, but you run into the undefined problem because cosecant x is equal to 1 over sine x. So therefore, as x approaches 0, 1 over sine 0 is undefined. So it's not a case of us getting 0 over 0. It's a case of us having an undefined numerator. So expression is undefined at x equals 0. However, that does not mean the limit doesn't exist. So this is sort of a special case. So for us to make any headway with this, we just can't throw it out and say, well, it doesn't work, it doesn't exist. We have to simplify it if we can and see where it takes us. And because you can do that with trig, because you are permitted, because first off, you've got, with the reciprocal functions, you've got some discontinuous graphs. So they will be undefined at points, but that doesn't mean the limit doesn't exist. And then you also have the ability to simplify them using identities. And that's what I'm sort of going to do with this one. Now we've got choices with this. If you have a group of 10 people who are fairly good at these, doing this problem, you'd see, at least a half dozen different approaches, all correct. So you basically have to turn yourself loose with it. But what I'm going to do, I'm going to start making some of these changes into the primary forms. Like cosecant, I'm going to write as 1 over sine x. And then the denominator, I'm going to write as 1 over cos x. And then up top, I'll write this as 1 over cos x minus 1. Now you might be tempted to multiply that 1 over sine in, and you'll get the right answer. What I'm going to do before that, however, is I'll take that 1 over sine x divided by 1 over cos x. I'm going to multiply that by cos over 1. And that's going to turn the expression into, get rid of our fraction, or our big fraction, or complex fraction, and have cos x over sine x multiplied by that numerator. And then if we get a common denominator in there, although this, some of you wouldn't even bother, you would just distribute it in. That's fine. So common denominator of cos x means that we get 1 minus cos x like that. And this is where we start to get some good things happening. The coses will divide out, and this becomes a limit as x approaches 0 of 1 minus cos x over sine x. And this is the first time we've seen a 1 minus cos set up. But that's good, because we can handle that. This can be broken up into 1 minus cos x multiplied by the sine x on the denominator. And then we introduce what we need. And what we need is 1 minus cos x, an x on the bottom, and then we also need an x on top for the sine x. Thing of it is, we don't have to introduce anything else because those two will cancel each other, take care of one another. And 1 minus cos x, first time we've seen that limit, as I said, this is equal to 0, and then times 1, which we have seen. So that's equal to 0. So this whole thing would be equal to 0. So that's kind of a nice way to do it. Not the only way. Some of you would use another method by multiplying by conjugates 1 minus cos x over sine x, and I won't take the time to do that. Hopefully we'll get another chance to see that type of method. So those are a look at some pretty standard ones. I think I'll just do the one more and then call this a day, because this tan x will come in handy, and then I'll finish these other ones later. Now tan x over x, if you substituted it in, you're going to get 0 over 0, because the tan of 0 is 0. Now what I'm going to do with this identity with tan x is sine x over cos x, and then all this divided by x. So when we divide this out, we get sine x over cos x multiplied by 1 over x. And then if you shuffle this one up, you can write it as sine x over x times 1 over cos x. So all I did was I took this x and I wrote it there. Same thing. Sine x over cos x times x. Just put the x with the sine. And this is good, because sine x over x is 1. And then 1 over cos x is 1 over 1 is also 1. So, in fact, what happens as a result of this, we just get 1. So keep in mind that the cos of 1, or the cos of 0, excuse me, is equal to 1. This is useful because some people will even remember that tan x over x is equal to 1 as x approaches 0. It's not on your formula sheet, but it almost made the cut. So it's worth filing it away someplace. So the next video clip will show the remaining ones on this set of questions, and then we'll move on to other things. A lot of people do find the limits trickier than anything else in the trig section, and it's understandable because you really are thrown out there. They're proofs in a sense because they're simplifications, but they do require you to be pretty good at these, whereas the other derivatives, for example, tend to be just sort of a formula-based thing. You don't have to think too much. Here you have to make decisions. But see what you can do, and I will talk to you later. Thanks for your time.